So, in the last lecture, we talked about Gaussian process, if you remember, and where we stopped was that we basically covered everything about vanilla Gaussian process, that how to compute the hyperparameter, and inference means computing the predictive mean and the predictive variance, because the inference will also be a Gaussian process, the predictive distribution will also be a Gaussian process, right. So, just to quickly recap, this is what we have discussed till now, if you think about it. What we started by considering that our function y t equal to y plus epsilon, which is unknown, is a Gaussian process, and we considered it to be a zero mean Gaussian process, right. So, that is what you see at top left, and then t given y came out to be a Gaussian distribution, because the noise was Gaussian, correct. From there we computed the, but our objective was to find out the, what is our objective in training? What we want to find out in training in Gaussian process? Hyperparameters, process variance, length scale parameter and the noise variance, three things, right. And you cannot do it directly by maximizing the likelihood. Why? Why can't you directly maximize the likelihood at top right? Because y is unobserved, you do not have any measurements of y. So, what do we do? Marginal likelihood, maximize it or minimize the negative log marginal likelihood, and marginal likelihood computation is shown in the second row, and that comes out to be a Gaussian process again, with some change in the covariance kernel, which is shown at the right. So, basically beta inverse I is added. Now, from there you can now maximize that negative log marginal likelihood, and that will give you the hyperparameters, process variance, length scale parameter and the noise variance, right. And once you have that, that is not our objective. Our objective is to make predictions. So, for prediction we need to compute the predictive distribution probability of t star given t. That comes out to be a Gaussian process again, and that we computed by partition of matrix and using the property of definition of Gaussian process, and that you derived last time. These two at the bottom left are your predictive mean and the predictive variance, and you derived it yourself in the last lecture, right. So, now in all of this setting, one thing that we will observe is that the covariance matrix Cn, you need to invert it again and again, right. For example, if I have to write down the, so in Gaussian process, our loss function L theta is n by 2 log 2 pi plus 1 by 2 log determinant of Cn plus half T transpose Cn inverse T, right. This is what we derived last time. This is our loss function, and if I have to evaluate this loss function, I need to compute Cn inverse, and I do not, and remember Cn inverse is function of your hyperparameter. So, when you are optimizing for the hyperparameter, at each iteration you have to invert this Cn inverse, whose dimension is n cross n, where n is the number of data point. What does it mean? It means that there are multiple times you have to do an inversion of n cross n, which is expensive. Not only that, if you want to predict, so even during prediction, so during prediction, if I have to compute, let us say mu t star given t, that comes out to be k transpose Cn inverse t, right. It comes out to be k transpose Cn inverse T, right? Is it K transpose or K? What is the dimension of K? N cross 1. So, it has to be K transpose, then it will be 1 cross N cross multiplied. Okay. And my covariance or the predictive variance comes out to be small c minus K transpose Cn inverse K, right. So, the take home message or the bottom line from here is that you have to again and again invert Cn, right. So, Cn inverse is to be computed, okay. And this is expensive because inversion of a matrix, the computational cost is the order of n cube. So, computational cost of computing Cn inverse is of the order n cube. Now, to put thing into perspective, let us take some values of n. Okay. So, suppose n is 1 million, which means I have 1 million data, which is not a big data in today's time. In today's time 1 million 10 lakh is nothing. So, if suppose n is equal to 1 million, if today one single CPU, modern CPU, if you try to invert that 1 million cross 1 million matrix, it will take 2 years, okay. Actually 2.9 years, 3 years. So, to put things into perspective, if n is equal to 1 million, we will require 2.9 years to compute Cn inverse. This is today I am saying. Now, one point of view or one way of attacking this problem is to improve the hardware architecture. That why can't I improve the hardware architecture, make the processor speed faster, and will that help? So, let us assume, just to give you some numbers, that we are improving at a rate of 20% per year. 20% is a very big number, 20% improvement in speed is a very good number. So, if we improve at a speed of 20% per year, okay, then 10 years from now, if you have to compute this inversion, that will take 172 days, which is still huge. I mean almost half a year, right, 6 months. So, assuming 20% annual increase in speed, computational speed, after 10 years, we will require somewhere around 172 days, okay, which is still huge for just 1 million data, okay. And 50 years from now, that will come down to 2.9 hours, which is still, I will say, is a big number. 3 hours is still a big number. So, if you can wait 50 years, then probably it will be somewhat manageable. Otherwise, increasing or improving the computer architecture, the hardware architecture is perhaps not an option. Clear? The point I am trying to make is clear that you have to do something with the algorithm itself. You cannot hope that the hardware will improve and let it be as it is, because you have to also remember that today itself we are working with billions of data. So, maybe by the time 2050, or 50 years from now, let us say, you will be working with, I do not know, trillions of data. So, your development of the architecture will not be able to match the development or the increase in the data that will be available. So, naturally the option that you have to explore is to come up with algorithms that can do these things in a faster manner. Okay. So, therefore, researchers are actively working on making GP scalable. Okay. So, that is why, so that justifies the need for working to working towards accelerating the algorithm, right? Clear? So, now the question comes, how can we accelerate it? Because remember that Cn is a full matrix, because you are computing it from your covariance kernel, which is, let us say, exponential of minus x dash, which will never go to because it is an exponential, that will never go to 0. So, basically what it can be small, but never 0. So, what you are working with is a full matrix in general, right. And if you are working with full matrix, you cannot really hope to make it or you cannot really hope to parallelize it until and unless you impose some assumption, approximation or some structure in your matrix forcefully, that will not come naturally. Okay. So, however, it is non-trivial to scale GP. So, basically in HPC terminology, I can say that it is not embarrassingly parallelizable. It is not. There are things which are embarrassingly parallelizable. For example, MCS, Monte Carlo simulation, because there the samples are drawn, you draw them together and then let them run on one CPU. No loss of accuracy, it is by default in a parallel mode. This is not. So, you have to impose some structure, some assumption, some approximation to make it run in parallel, or rather to make it scalable. The important thing is to make it scalable, right. So, that is the whole idea. Clear? So, so sparse GP can be thought of as a class of algorithms. So, it is not just one algorithm, it is a class of algorithms that scales or that tries to scales maybe GP. And our objective today is to talk about different ways of scaling it. So, we will not talk about one way of scaling it, we will talk about different ways of scaling it, and it is necessary to talk about different ways of scaling it just because every scalability route I will take will be based on certain assumption, and if those assumptions do not hold, the method will fail. So, naturally there are different assumptions that you can take, and each of those will result in some scalable version different from the other. Clear? So, the first thing that we will talk about is low rank approximation. Low rank approximation. Okay. So, any idea what is low rank approximation? Anyone has any idea? Have you heard this term earlier? What is it?
It's m into n matrix into m into 1 into n into 1.
Not one, but some reduced form, right. So, the idea is that you will have to somehow reduce the rank of your matrix. Your matrix cannot be full rank. And if you can reduce it, you can represent it as product of two rectangular matrices of dimension, let us say n cross r and r cross n, where r is much less than n. And if you can do that, then I will show you that with that setup you can now invert it as at a cost of O of r cube instead of n cube. Actual cost is n r square, but anyways I will call it r cube. Okay. So, the idea here is to represent k as using low rank approximation. Okay. So, the idea is to represent k, and k is our original covariance matrix. So, that plus sigma square I am not touching, only k is what I am working with, because sigma square I is anyways the noise part, I cannot touch it. So, mathematically it means that k will be approximately equal to k star, which is xi transpose, capital Xi transpose. Okay. Okay. Where xi is n cross r. Okay. So, here we are assuming that r is the rank of the matrix and r is much lower than n. So, we have also assumed that r is much less than n. Okay. So, this is, I am not yet telling you how can we find out this xi, but let us say we can find out this xi. How to find out this xi will form the different algorithms in low rank. Okay. So, k star is equal to xi transpose, where xi belongs to n cross r space, okay, a matrix dimension. So, now if this is the case, then what is Cn? So, therefore, what will Cn look like? Cn will be equal to xi transpose plus sigma square I or beta inverse I, right? Correct? And I want to invert it, which means I want to invert this whole thing, but the dimension still is n cross n, because even if k is low rank, you cannot guarantee that k plus sigma square I will be low rank, most probably it won't be, correct? So, now do you know any theorem that can help us solve this from linear algebra? Maybe you have derived it, I do not remember, but maybe in one of the practical or homework it was given. Derivation. Woodbury matrix inversion lemma. There is one theorem which is the Woodbury matrix inversion lemma. So, let me quickly write down the lemma. Woodbury matrix inversion lemma. Okay. And it basically takes the following form, that suppose you want to invert A plus UCV inverse. So, it has to be of this form. Okay. If something can be written of this form, then this is equal to A inverse minus A inverse U C inverse plus V A inverse U V A inverse. Please verify this. I think I have written it correctly, but please verify it. Most probably it is correct. Okay. So, this is how you can, this is basically the matrix inversion lemma. If you have something of the left hand side form, you can write it, it is equivalent to writing it in the right hand side form. Okay. There is one mistake I can see immediately, there is an inversion here. Okay. Okay. So, now I want to use this to this. So, how will I use it? Do I need to make any changes? Do I need to make any changes? Take a look at the last equation and this one, the left hand side. Can you figure out that if there is any change that I want to make or I need to make? See, it was UCV. In this case, the C is missing. So, what will be the C for me? Identity I. And what will be the A? Right? Now, remember that whatever A I take, I have to invert it. Taking sigma square I as A is beneficial because diagonal. So, just invert the element, not costly. Right? So, that is why always select A as something that you know that you can invert. That is the trick. This is only useful when A is easily invertible. And dimension of U and V and C is, and dimension of C is less. This is only useful when A is easily invertible and dimension of C is less than the overall dimension. If dimension of C and A are same, then it is useless. Okay. So, let us see how does it work. So, this I will rewrite it as sigma square I plus I transpose inverse, right. Now, take a, this should be I n. So, that means a n cross n identity matrix, whereas this should be I r cross r identity matrix. Look at the matrix dimension, it will make sense, because xi is n cross r multiplied by r cross r multiplied by r cross n, right. Any question? Okay. So, now I am ready to invert it. Sigma square I n is my A. So, then this will be equal to, so let us call it equation 1 maybe, 2. So, using 2, 1 reduces to Cn inverse is equal to sigma square I inverse minus sigma square I inverse, then you have U is xi, then you have sigma IR, right. So, C inverse will be what? IR plus you have xi transpose A inverse, right. A inverse is equal to sigma square I inverse, sigma square I inverse xi whole inverse, then you have what? Xi transpose sigma square I inverse. Okay. So, now you tell me what is sigma square I inverse. I inverse is I, sigma square inverse is beta, precision, beta, right. So, I will write it as beta I minus, from here I will get one beta, which is beta is a scalar, remember that. From here I will get another beta. So, I can write it as beta square. So, minus beta square xi, IR is IR plus, from here I will get one beta scalar, I will bring it outside, I will remove. So, beta xi transpose xi inverse xi transpose, then done, right. I and all those things that you do not need to write them. Okay. So, now what are the matrices you are inverting? There is only one matrix you are inverting, right. And what is the dimension of that matrix? R cross R. So, I have reduced n cross n to R cross R, that is why it is known as low rank approximation. Okay. So, this whole thing is R cross R, clear. Any question? You should ask one question. How to compute xi? I have not told you, right? So, this does work in theory. So, this works in theory given we know xi, right? But the question is how to compute this xi. Theoretically, xi can be computed by solving a minimization problem, solving an optimization problem. So, now you tell me what this optimization problem should look like, common sense. So, so you will have to, xi theoretically can be found out by solving an optimization problem, right? But the question is, what do you think this xi or what do you think this optimization problem should look like? Can you think of something? What are the, what is the ideal xi, if I may ask you? What you think is an ideal xi? As close as possible. So, my objective function should be some norm between this, correct? Anything else? The rank of this k that you are getting by xi transpose should be at least at max r or less than that. It is no use if the rank is high. So, that means it is a constrained optimization problem, right. So, basically you can think of it like this: k star, suppose I want to find out, is equal to argmin k tilde some norm between the k that you know and k tilde, okay. And there is a special norm for matrix F free for, yeah, right. Norm subjected to rank of k tilde is less than equal to r, right. This is the optimization problem you have to solve. One question, how does this norm look like? So, let me also give you that, where k tilde is basically equal to xi transpose, okay. Because if you can reduce the rank, if you can find out k tilde whose rank is less than r, you can always find out xi transpose, then it is straightforward, right. Yeah, one last thing is that, suppose I have a matrix and I want to find this norm, this is equal to square root of trace of A transpose A, okay. That is the definition of this norm, okay. Basically, the trace of the matrix you take and the inner product and then do the square root, okay. So, that is the definition. But in practice we do not use this, this is in theory, that is why I wrote theoretically. So, now can you suggest some easier way of doing it? We may or may not do it, but can you think of some way of finding out k star or k star, yeah. Maybe whatever you suggest may be a solution to this method. I do not want to solve this method, but I want to see if you can come up with some method based on your previous knowledge of previous course of finding out k tilde or k star. Can you think of something? Generally, you can, you study this concept that I will talk about, the answer to this you generally know from your second semester. UG second semester. So, that is a clue. And if you have done a vibration course, it is done in even in vibration course. So, it is all related. Eigenvalue decomposition, right? You can do eigenvalue decomposition and then ignore the higher order eigenvalues or the eigenvectors and then write it in terms of the remaining eigenvalues, and that will reduce the rank of the matrix. But we do not use eigenvalue, we use singular value decomposition, which is a stable way of doing things. So, in practice, this can be achieved using singular value decomposition. Okay. So, basically you have k, using SVD of k we can write it as U S V transpose, where S is the singular value and U is the singular value matrix or singular vectors, right. And then your k star, if you have to find out, let us say you want to reduce to R, so you will select only R. Basically, assuming things are arranged in ascending or descending order, mostly descending order. So, basically take only the singular values which have significant influence. Those are smaller singular values you can truncate. Similar to smaller eigenvalue you can truncate. The larger eigenvalues have the maximum energy contribution to this. And if you do this, you will get it. Once you get it, after this what will you do? After this, once you have done this, you will calculate your Cn, which is equal to sigma square I plus UR SR VR transpose, and if I have to do a inverse. So, from here you will get sigma square I inverse, which is beta I minus, you will get a beta square, then you will get U is UR, and then inside SR inverse plus VR transpose beta UR inverse VR transpose. Something like this you will get. I just use the Woodbury matrix inversion directly, when all the beta and all those things combinations I did directly. Okay. And here SR is R cross R, so you can invert it, right. VR transpose is R cross N, UR is N cross R, so that will again give you R cross R. So, everything becomes R cross R. So, you can now invert it at a cost of N R square or R cube, let us say. Okay. I mean the actual number is N R square, but let us say R cube. Any question? What we did? Clear? Same thing. Now, what is the problem with this? Can you tell me whether, do you see any potential issue with this method? Do you see any potential issue with this method? The potential issue with this method is that if you try to do a full eigenvalue decomposition or a full singular value decomposition, the cost is n cube. So, if you try to do and then truncate, that does not help, because you are back to n cube cost. But there are efficient algorithms of doing it, where let us say you pre-decide R and then locally optimal way you can find out the only the first R leading eigenvalue, and you can do it. So, you can use it in practice, but do not imagine using it just by using let us say the EBD command in MATLAB or in Python. It will not work like that. You have to use some optimized algorithm for doing the singular value, because computational cost of singular value or eigenvalue is also n cube. So, that kills the, that creates the problem or kills the whole purpose. Okay. Clear? So, this is one of the method that we discussed in load and approximation. There is another method. Okay. So, an alternative approach is to express the covariance matrix using basis function. Okay. So, this I very loosely touched upon this in the last lecture when I said that any covariance kernel can be represented as outer product of basis function matrix. So, basically your K can be, you can think of K as psi transpose, where this is basically your basis function matrix. Okay. So, now, so basically this is how your linear regression relates to kernel regression, because whatever results you get in linear regression, that is using basis function. So, from that, if you can directly calculate this kernel and you can relate it that there is a one-on-one relation between kernel method and linear regression. Okay. Probably in APL 405 it might have been covered, I am not very sure, but there is a direct relation. So, now suppose my y is expressed using R basis function, y is expressed using R basis function, W transpose phi x. So, there are R basis function. Okay. In that case, what is the dimension of this xi, assuming n data point? N cross R, because data point goes in row and each column is one basis function. So, phi 0, phi 1, phi 2, phi r minus 1, right. So, if you remember, psi basically is of this form, right, psi 0, psi 1, psi r minus 1, and this is the data direction. So, basically this is the basis direction, and this is the data direction, right. This is how you write basis function in linear regression. Throughout whatever you have done, this is the function you have used. Obviously, we are using capital phi as a notation, now I am using psi, that is a notational difference, but this is what you do. Any question on this? Clear? So, now if you take R basis function, automatically your kernel, the rank will be R. So, you will automatically get a reduced rank matrix if you use only R basis function. Clear? What is the problem of this method? The whole motivation was not to use basis functions, we are back to that. So, I motivated GP that I do not want to use basis function. We are back to what we started with, right. So, not preferred probably. Some cases we have to use it, but mostly not preferred. Okay. However, this necessitates selecting basis function, which is what we wanted to avoid at the beginning, right. But then why did I discuss it? Because there is one variant of this which is very useful and people have been using it, which is the spectral low rank GP. Okay. So, one popular variant is the spectral low rank GP that uses this technique. Now, can you this technique means technique of basis function. Okay, so that technique means basis function base. So now, can you tell me what spectral means? Have you heard the word spectral earlier? Oh. When do you use the term spectral? Eigenvalue, that is one answer. Anything else? So mostly when you use Fourier basis, sine cos. So that is the main. So eigenvalue that we are saying, that becomes equivalent to using this Fourier, because e to the power it comes, and that is can be sine and cos. So in that sense, okay. So mostly when you use the sinusoid basis or the Fourier basis. So then what is spectral low rank GP in your opinion? You use the Fourier basis, and then using that you formulate k, and then that is already a low rank because you are truncating the basis, and if you do that, that is the spectral low rank GP. So this uses Fourier basis, which is the harmonic basis basically. Okay, so sin cos, sin 2x, cos 2x, sin x, cos x, all those things will come. Clear? So this concludes our discussion on low rank approximation of GP. Okay. What is the idea? Let me summarize. What is the idea of low rank approximation? The idea is somehow reduce the rank. People might have done 10 things, you can be the one to do the 11th thing. You can come up with your own idea of reducing the rank. If you do that, that will be a low rank approximation. Clear? Any question? What is the issue of low rank? The issue is itself that how are you reducing it, that itself introduces some error, some assumption, some approximation into your whole calculation. Clear? So next, there is another method. Remember, all of these are subset of again sparse GP. So we are talking about how to make GP scalable. Low rank is just one way of making GP scalable, but there are other methods also. And the second class of method, or rather I will say one second method, maybe not class, is the subset selection method. Subset selection method. Okay. So what do you think we do here from the name? We select subset of training data. So if I have n training data, I will select r training data among those, and somehow by combining this n and r, I will write my covariance matrix. Okay. So we select r training data. So this is basically the subset from the available n. This is the total. Like I have 10, I will select 2. So then n becomes 10, r becomes 2. Clear? Now you also need a way of writing k that is kind of tractable. So k is approximated as so k, let us say approximately equal to k star is equal to k z inverse k z transpose. Okay. I have not yet defined what is this. So let me come to that, and then it will start making sense. So first of all, tell me what is k. I will, okay, before I write k, my training data, let us say, is of this form, right. So this is my training data, I am just keeping it for reference. So, now tell me what is k? What is k? The leftmost covariance kernel between what? How do you compute k? You take all the input x, so k x comma x prime, that is what you write. So, this is k x comma x prime, and what is the dimension? What is the dimension of this k? N cross n. Right? What is kz? Kz is k x comma z. What is z? Z is a subset from here, a subset. So, z is xi comma ti, but I now goes to 1 to r, and whatever xi is here I will call it z. So, basically you select a subset from there and you call it z. Okay. So, then what is the dimension of this? Tell. N cross r. N cross r. What is kzz? Zz. So, z comma z dash or z prime. Dimension r. Okay. And z transpose is r cross n. Right. So, now what do you think will happen? What do you think will happen if I take r to be equal to n? So, basically my subset is all the training data. If I take that, what do you think will happen? What will be kz equal to? If r equal to n, z is equal to x. K, repeat. Kz will be equal to k, kzz will be equal to k. So, basically the right hand side will become equal to the left hand side. K inverse k and k inverse will cancel out, you will get a k. So, this shows that this is a valid approximation, because as r tends towards n, your accuracy of k increases, and at r equal to n you get the exact covariance matrix. So, one of the questions that should come to your mind is that how is this approximation even valid? So, this shows that this approximation is valid, because as r goes towards n, your left hand and right hand become exactly equal, so the approximate sign goes away, which means increasing r increases your accuracy. So, this approaches the exact k in some sense, right. I will not say asymptotically, I do not know that, but it approaches it. Okay. Clear why is it a valid kind of approximation? So, now okay, let me write it down. So, as r equal at r equal to n, k becomes equal to k star, which is equal to k inverse k, which is equal to k, right. Clear? So, now I have to compute. So, with this setup, my Cn is equal to, what is Cn equal to? Cn is equal to k plus sigma square I. So, k will be replaced by k star. So, it will be sigma square I plus k star, which is equal to sigma square I plus kz inverse kz transpose, and then if you have to find the inverse, it is the inverse, and again we are back to our Woodbury identity kind of form. So, that is why Woodbury is a very important, that is why I gave it earlier, most probably I do not remember, but because you will need it throughout this course, okay. Specifically if you have to do something analytically. So, this is then equal to beta I minus sigma square I inverse. So, that will be beta. So, beta and beta from right hand side will give me beta square, and then k z, and then k z z inverse is k z z. So, even you do not need to compute the inversion now, that k z plus k z transpose, there will be a beta coming here, k z inverse k z transpose, right, from Woodbury identity. You get this? Clear? Which means again you have to only invert a R cross R matrix. So, you have to only invert a matrix of the size of your subset, right, and that is why it is known as subset selection method, because the better subset you select, the better will be your accuracy. Any question on this, or is it clear? So, if it is clear, then you tell me what is the limitation of this method. Can you see some limitations? Selecting R, or rather selecting the subset. Selecting R may be still easier, that how many data point I want, but which data point. From N, if I have to select R, it is NCR, right, but which of this NCR combination, 1 by NCR, that is the probability of one subset. So, which subset should I select, right. So, the challenge is selecting or deciding which subset to select, right, and not only that, your result is a function of that. So, for some subset you might get a good result, for some other you might not get a good result. So, the challenges are which subset to select, and the other one is that it overfits the subset, because whatever subset you select, it totally trained based on that, and it might not generalize to other subset and all those things, right. Clear? So, now how do you think this can be addressed? How do you think this can be addressed? There is a very layman way of addressing this. So, can you think of that? So, then it is very expensive, NCR, but that is also a solution. Anything else? Maybe you can think of formulating an optimization problem to select the subset also. So, it is not only finding out the hyperparameter now, but also finding out the subset. So, try to develop a optimization problem, which will first select R points from your training set itself, and then solve the problem, and then try to optimize over that R, which R to select.
So, but then the optimization, then the computation cost also will be?
It will be less than computing all combinations. So, computing NCR combination is much higher than, because optimization might take 20-50 iterations. So, you have to do 50 times, whereas NCR will be much larger, specifically if N and R are, let us say R is somewhere midway between N. So, let us say R equal to N by 2 and N is 1 million. So, let us say 1 million C 10,000. So, just imagine what will happen. So, compared to that, optimization will always be faster. Okay. Clear? By the way, this optimization algorithm was actually utilized, but not within this, but within the next algorithm that we are going to talk, which is an extension of this, and the idea is very simple. Why? Okay, first you tell me what does k z depends on, k small z, I mean one single z. What does it, how do you calculate k of z? Yeah, but what does it depend on? Does it depend, because I will go back here. So, look at the data, does it depend on t is the question I am trying to ask. So, last lecture we already discussed it in length that it does not depend on t, it only depends on your input, correct. So, that means for computing kz, what do you need? Only x. Do you need y or t? Correct? At least for k you do not need. So, then why is it necessary that the subset has to be selected from the training data only? Why can't I select some other points where I have some new x? I may not know the t at that point, but I know the x at that point. Is that not possible? Think about it. So, suppose let us take 1D, right. So, this is my x and I have 1 point, 2 point, 3 point. Okay. So, 3 x point I have and at this 3 I have y, y1, y2, y3. Okay. So, now I am saying that select a subset of 1 from this. Why is it necessary that you have to select either these or these or this? Why can't your subset have a point which is here? Because that x point you will know, y point you do not need for computing k, at least in theory you do not need, right. So, then why is it not possible? And this is what people observed, and they came up with a method known as pseudo input based Gaussian process, because these inputs are like pseudo inputs. Why pseudo? Because you know x but you do not know t. I will give you a minute to process this, because this is something now different route I am going, and see if it is making sense or not. If not, please feel free to ask question, I will be happy to explain again. Is it clear? No, okay. So, what I am saying is that whatever k you calculate depends on only x and x dash, clear. And what is x? X is your input. Now, input you are free to generate as many as you want, and for any input you can find out k, you do not need t, correct. This part is clear, right. So, now we have previously represented k star as kz, kzz inverse kz transpose, right. This is what we have done. The question is, why kz, which is equal to k of x comma z, why this z need to be a subset of x? Why can't it be some other point which is not a subset of x? Yes, that value of that point you will know, or you will need to know, but that you will anyways optimize for, and the value of t you do not need, at least in theory you do not need it for t, right. So, can't we do that? Now is it clear what I am saying? So, the idea is this z is a subset, but that subset it need not be a subset, it only need to be some points which may or may not be in the training set. If it is in the training set, it is well and good, but it need not be in the training set. Okay. So, this was, so the question was why z has to be a subset of x. K only depends, k only depends on x, or rather input, and not the target. Yeah. What is the benefit? Good question. So, think about it. I said that you will like to select Z, right? And how will you select it? By optimization. If you are limiting yourself to the training data, that is limiting your option. None of those points may be optimal point. As a result, you might need a higher value of R. Whereas, if you allow Z to be any point, you may potentially reduce R even further. So, the advantage is to reduce R further or to reach the optimal point. Okay. So, K only depends on input and not on the target, right. Based on this, pseudo input based GP was proposed. Okay. And remember, this pseudo input based GP is nowadays, this is what people know as sparse GP. Although I said, and I will still stand by that all the methods I discussed today are sparse GP or are within the falls within the larger class of sparse GP. But many people, if you tell them sparse GP, by default they will think about this method only. Okay. And this pseudo inputs has a name, they are known as inducing point. I will come to that later. So, okay. So, I will not be able to complete it today. So, I will just start it, and maybe in the next lecture we will again start from this point only. Okay. So, here we have training data which is D, which is x comma t I equal to 1 to n, and also pseudo inputs which is D z I comma u I equal to 1 to r. Okay. What is u I? The output corresponding to z I which we do not know. So, that is why these are pseudo input, z I are the pseudo input, u I are the responses corresponding to pseudo input, but we do not have any measurements, we do not know them, but had we measured we would have got, or we would have measured u I or something like that. Clear? So, u I are the pseudo output, z I is the pseudo input, x I and t I is my training data. So, I will repeat again this portion. So, D anyways we will always will have in machine learning, which is x I comma t I. We are also introducing a pseudo input which is z I, and corresponding to each z I we have u I. Okay. Now, u I we do not know, those are like hidden variable, unobserved. So, we have to do something about that, but z I we will anyways optimize for, and we can always measure, and z I can be anything. The u I we will never know. Clear? So, now where is x I and t I coming from as per our assumption? From a GP. And where is z I and u I coming from? The same GP, because we are trying to, there is a function we are trying to learn. So, x I and z I are from that input to that function, t I and u I are output to that function, from that function. u I we do not know is a different story, but that is the output, or that is supposed to be an output, or that is supposed to represent the output. Clear? So, then can you tell me what is probability of t I u I? What will be this distribution, or not t I, sorry, t and u, t and u. What is the probability of this? Given that these are from GP, what is the distribution? What is the distribution? Forget about u, if there is only probability of t, then what would have been the distribution? Louder? What? Multivariate Gaussian, right? Why? Because they are from the definition of GP, any finite collection from a Gaussian process will be consistent Gaussian distribution. Now, U is also a finite collection from that GP. So, then this will also be a multivariate Gaussian. Okay. So, now same logic, T U, what is the mean as per our assumption, as per our prior probability of y, what was the mean of probability of y? 0 mean Gaussian process is what we are working with. So, this will also be 0 mean. And covariance, this is important, this you tell. What is the first? It will be 2 cross 2 in the way I have written, each of those. So, what is the first element? What is the covariance when you find a probability of t? K plus sigma square I, we write it as Cn. So, K plus sigma square I, we write it as Cn. Okay. What is the second term? Okay, we will not write it as Cn now, but for now I am writing. What is the second term? Covariance between T and U. So, actually not T and U, it will be KTU, but between x and z. Between x and z, but we will write it as KTU. KTU, then here K TU transpose, and the last one you tell, this one. This is interesting. What should it be? K? We are not using star, we are using KUU. So, will it be KUU or KUU plus sigma square I? That is the question. Because remember there is a diagonal there. So, do you think it will be KUU? Because KUU is like K in the first diagonal term, or do you think it will be KUU plus sigma square I? It will be one of these two, which one and why? Common sense will tell you plus sigma square I, right? But that is wrong. So, why is it wrong? So, I am also giving you the answer. Answer is KUU. No, sigma square I will not be here. So, can you tell me why sigma square I will not be here? What is KUU? Where does sigma square come from? Noise in what? Target. Now, U is what? Have we measured them? So, if you have not measured them, where is noise? Where will noise come from? Because those are pseudo, right? We have never measured U. So, if you have not measured U, where is the point of noise? So, that is why that sigma square for that is 0. Clear? So, no sigma square I as U is not measured. Okay. Clear? Any question? So, one notational change, K plus sigma square I, we are till now writing as Cn. Now, this will be written as K. How will I write it? K Tt plus sigma square I. Why Tt? Because K was covariance between the x and x, in this case T and T. So, that is why. To give you more, so now you tell me what is KTT equal to? It is equal to K x comma x dash. KTU is equal to K x comma z. KUU is equal to K z comma z. Clear? I wrote it specifically because you should not get confused with u. There is no u in the covariance calculation thing. It is only the input. We are writing because the distribution is over u, but you calculate it as a function of only z. So, now you tell me what are the unknowns? What are the unknowns here? What are the unknowns? And this is the last thing for today. I will stop here. What do you want? What will you train for? If I may rephrase the question in machine learning terminology, what do you think you will be training for? What will you train for? Repeat.
Like values of u.
U. But u is not there in your function. So, what will you train for? First tell the obvious ones. In GP, what do you always train for? Hyperparameters. What are those? Sigma square, sigma p square, L. So, those three are obviously there. Sigma square, sigma p square and L. These three will always be there. Along with that, is there anything that is unknown? R I will fix. So, R is hyperparameter of hyperparameter. So, anything else apart from R? Z, you do not know Z. I said Z can be anything, but what is that thing? The pseudo inputs, do you know those? What are the value of Z? You do not know. So, also Zi. So, then how many unknowns now? Not 4. R plus 3. Zi is I equal to 1 to R. Total is R plus 3. How do you think we will train for it? What will be our loss function? I will not write it down, we will do it next class, but just to complete the loop. What will be your loss function? Do you think this will be your loss function? This one? This cannot be because u is not measured. So, we have to find out the marginal of t by integrating out of u, right, and from there we will find out the. So, we will do that next class. Last question, this form, was it new or had you seen it earlier? This form that I wrote here, the last thing of this slide, have you seen it earlier or this was new? Where? Prediction, last class, prediction was exactly this form. So, whatever prediction formula we use will be used in next class to derive the training loss function. Okay. So, just to conclude, we are talking about different types of sparse GP. We talked about low rank approximation subset, and this is the last thing we have started, which is pseudo input. Next class we will finish pseudo input and discuss variational GP, sparse variational GP rather, and that will be it for GP. Homework has been uploaded, please check it, yesterday I uploaded it. Okay. The last homework will also be uploaded in 3-4 days, and both deadline will be almost same. November 10th is for this one, other one will also be around the same time. Okay. So, we will stop here, thank you, and Wednesday whether I will take a class or not I will let you know. I mean practical will obviously be there, but what I meant is that I missed 2 lectures, one I have made up for, one is still remaining. So, the remaining lecture I might